from our previous section, we talked about the idea that if the value of the derivative is positive, that implies that the function is increasing on some interval. And if the derivative of the function is negative, that implies the function is decreasing on some interval. And if the value of the derivative is 0, that implies the function is constant on some interval. So usually we can't think about these in terms of just a point, we have to think about them in some interval. Otherwise, if it's at a point, then 0 might just be like a maximum or minimum. And usually speaking, for a continuous function where the continuous derivative and positive, it's a whole different bag, so we won't worry about that. But anyway, the first problem, we want to find the open intervals on which f is increasing or decreasing. So what I'm going to do is I'm going to segment this. I have to say, okay, well, it looks like it's decreasing here. And it looks like it's decreasing here. And then it looks like it's increasing here, and this looks constant. So if I'm going to answer this, I'm going to say that it's increasing 1, 2 on 2 and 3. And I'm going to say that it's decreasing on 0, 2, unioned with, so that's 1, 2, 3, 4, 5, 6, 7, 8. 5, 8. So that's just a simple way of reading a graph and trying to determine its increasing and decreasing intervals. And if I wanted to find just the largest of these, I would say that this is the largest interval where it's increasing, and this is the largest interval where it's decreasing, because that has a width of 3 and that only has a width of 2. So instead, if we have an explicit function given, f of x equals negative x minus 3 quantity squared, and we have its graph, well, let's estimate the intervals of increase and decrease, but then let's actually solve for them. So in this particular case, it looks like the function is increasing here and decreasing there. Now, I want to be careful, because this arrow here tells me that this function continues on. And this arrow here tells me this function would continue to go downward. But it can be tricky because I'm drawing an arrow in an opposite direction, and it's just because this is just telling you about the continuation. But if you were to look without it, you're just saying that as x values go from left to right, the function values increase. So I would estimate that this is increasing from negative infinity to positive 3 and decreasing from positive 3 to infinity. That's my estimate. So the way what we want to do is we want to do this analytically by using the first derivative test. In doing so, we would say, all right, the first derivative, by the chain rule, we bring down the power, we subtract 1 from the power, so that's a 1, so that really don't need that there, and then we take the derivative of the inside, which is just 1, so this is my derivative, negative 2 times quantity x minus 3. Now what I notice is that when x is 3, the derivative is 0, so I have a critical number there. But let's think about the values less than 3, and let's think about the values more than 3. So if x is less than 3, then x minus 3 is negative, right? Because the thing about that is subtract 3 from both sides. So that tells me that if I multiply by a negative value, I actually have to swap. Remember how inequalities work? If I multiply by a negative value, I have to swap. So that tells me that if x is less than 3, the derivative is positive. Now you could have done this more easily by just plugging in something like 2 or plugging in 0 just to get a value there. And that would be perfectly fine. If I plugged in 0 here, I'd get negative 2 times negative 3 is 6, which is positive. That's perfectly fine. So that tells me that it's increasing there. If x is greater than 3, x minus 3 is positive, but negative 2 times both sides tells me that it flips values. And again, you could have accomplished this by plugging in like 4 here. You would have gotten 1 times negative 2 is negative 2. It's negative. That's perfectly fine. So we would say that because of that, we have determined that our estimate is actually valid, which is kind of nice. Just go ahead and kind of prove it there. Now, what about this? X minus 4 quantity squared with the reciprocal. Well, if I look over here, I have an asymptote, so let's see. But it looks like as x goes from left to right, the function values increase. So I would assume this is increasing. And as the function values go from, or as the x values go from left to right, the function values here seem to be going downward, decreasing. So I would estimate that this function is increasing on negative infinity to positive 4 and decreasing on 4 to positive infinity. But we need to analytically look at that. So we need to take the derivative here. Well, the first thing I would do is I would say, all right, I'm going to rewrite g of x. Rewrite it to the negative 2 power. So then when I take the derivative by the chain rule, I bring the power down, I subtract 1 from the power, and then I multiply by the derivative of the inside. Well, the derivative of x minus 4 is just 1. So that gives me negative 2 over x minus 4 cubed. So we can follow a similar process that we did up here. We can say, well, first of all, what you notice is if I plug in 4 there, the derivative is not defined, which tells me that 4 is a critical number. However, since the derivative is not defined, we can't just, well, there's going to be another test we can apply there, and we can't apply it there because it's not defined. But we'll just have to start plugging in values or start analyzing intervals. So if x is less than 4, then x minus 4 is less than 0. So x minus 4 cubed is also negative. Which, by the way, you could say that to the negative 3 is also negative. You have to be careful. So what that tells me is this quantity is negative. So if I take this quantity and take 2 over it, tells me it's going to be positive. Now, I kind of had to cheat because the way we normally would do this, you would take the reciprocal of both sides, and if you do that, you still have to flip the symbol. But we can't really take the reciprocal of both sides here because we don't have, this is a 0. So what you do is you exploit the fact that if you know this is negative and you multiply by a negative, it's going to be positive. So if we do the same thing with x being less than 4, or sorry, x being greater than 4, we get that. And it's going to follow directly from the fact that the symbols just follow the same pattern, but they flip it, you know, they're flipped. So anyway, what we determine is what we estimated about it. So estimating from graphs is really powerful, but what if we have functions for which it's hard to produce the graph. And we can maybe do it with technology, but it may be hard with technology. It's easy when the numbers are 2 and 3 and 5, but even with technology, it can be difficult, because what if the number is 2.78446? And that may not matter. You may say, well, it's close enough. Well, in reality, it usually isn't. In reality, when you're dealing with simulations and you're dealing with timing, if I'm an autonomous car and I'm trying to determine at what point do I want to actually move over, well, I need to be pretty precise there. I don't need to be just kind of eyeballing it. So it's important to be able to use techniques to reduce our ability to, or to reduce the need to rely on just eyeballing things to figure it out.